All right, so this video is going to be on benzene's unusual stability as well as some factors that can help define aromaticity. Okay, and so let's start with a couple comparisons and heats of hydrogenation. So we know we have cyclohexene, cyclohexadiene, and then we have benzene, right? So each one of them has an extra pi bond. And we hit it with H2 and palladium on carbon. So hopefully you know this is a reduction process that adds hydrogens across the double bonds, right? Now, if we were going to do cyclohexene, then we would be given a value. I guess the heat of hydrogenation, sorry. So we release 120 kilojoules per mole when we hit it with H2 and palladium on carbon. So we would expect maybe double that for the cyclohexadiene, right? But we don't see that. We see 232 kilojoules per mole released, right? And so we contributed this to the conjugation of those pi bonds. Now, if we apply the same logic to benzene, we should see negative 360, but we know it's conjugated, but it's not only, it's super conjugated, and it's got minus 208 kilojoules per mole for its heat of hydrogenation. So that's actually even lower in energy than the cyclohexadiene, right? So benzene is just extremely stable. I say super stable. It's not like that's just my term for it. It's not actually defined as super stable. It just is very stable. And this is characteristic of aromatic compounds in general. When you have an aromatic compound, they are very stable, and their reactivity is a little bit different than what you would expect. Okay, so it's like anomalous, and so what we should be able to do with this information is kind of answer questions like this one. So, which compound has a larger heat of hydrogenation, and which one is more stable? Okay, so we would be given a couple compounds, right? So this is methylbenzene or toluene. And then we also have this this triene as well, this cyclic triene. And they both, after hydrogenation, yield methyl cyclohexane. So we want to determine what's the larger heat of hydrogenation and thus what is more stable, right? If we drew this graph, or a graph rather, relating the energies, right? We've seen this before. So the end product's the same, so they're both going to methyl cyclohexane, but the one on the right is actually lower in energy to start, and so that means it's more stable, right? And that also means that delta H is lower because it's the magnitude the difference in magnitude is smaller. So that means the one that is more stable has the lower delta H, right? So the larger heat of hydrogenation is going to be the one on the right. Okay, so the smaller one is the benzene, the toluene that's circled, and then the larger heat of hydrogenation is on the right. And so we can see that it does have four pi bonds, p orbitals in a row, and so that it is conjugated, but that's only for the top portion, and then the lower alkene is not conjugated. So if we were to estimate the numbers for the heat of hydrogenation for each of these, we would get about 230 for the top portion, the conjugated diene, and then 120 for the lower alkene. And so that adds up to about 350, which is larger heat of hydrogenation than the benzene. And so that's definitely expected, right? The more stable one is that benzene. And the reason being is because benzene is aromatic. And so what we want to do is kind of lay out the criteria for aromaticity. And one of the main components is going to be Huckel's rule. So whenever you talk about aromaticity, you want to talk about Huckel's rule. And Huckel's rule is basically a way to identify if something is aromatic, but you need all four of these criteria that I'm about to give you to be met. And so if a molecule is going to be aromatic, then it must be cyclic, it must be planar, it must be conjugated, and it must have, if it has all of those, then it must also have 4n plus 2 pi electrons. And so that's Huckel's rule, that fourth one. The 4n plus 2 pi electrons, provided all the other three criteria are met. Then you can determine if something is aromatic. And if something's aromatic, then it's going to be anomalously stable, like that benzene. It's going to have different types of reactivity like benzene. Okay, so it is important to define if something is aromatic. So if something is cyclic, right? Obviously, it's got to make a ring. So the benzene on the left is cyclic, cool. The compound on the right, however, it looks just like benzene, but it's missing that last sigma bond on the right. And so it doesn't quite have the 6p orbitals all in a row like benzene does. So we've got, I'm going to draw the blue first, sorry. Boom, boom, boom. We have 6p orbitals all in a row, but they're not completing a circle. So the first p orbital and the last p orbital, they don't overlap there. And so the stability associated with aromatic compounds is not there for this, what is this, hexatriene. And so defining if something is cyclic is really easy, right? But when to defining if it's planar is a little bit more difficult, because we're dealing with two dimensions when we're talking about chemistry most often, right? And so typically what you'll be given this information. So there are a few things that you should know are planar, and those are the things that we talk about. Okay, so otherwise, if you're given a question about this, then you would be told if it's planar or not. Okay, it's usually like, oh, provided this molecule is planar, then is it aromatic? And that gives you other things, right? So this cyclooctatetraene is not planar, okay? And I'm telling you that now, okay? I don't have to tell you ever again because you know that now. So cyclooctatetraene looks like this on the right. It's kind of like it looks like that. I don't even know what that would look like. It's an uncomfortable beach chair. So it's not planar because let's see, we have these p orbitals right here where they're overlapping. And sorry, I'm going to just draw this red in real quick. All right, so the bottom p orbitals, those are parallel to one another and they're overlapping. The upper p orbitals are angled, obviously, so their overlap is very poor, especially like with that blue portion of the orbital. There's not significant overlap or none at all. And so that's why that's pretty much why planarity has to be achieved in order to have something be aromatic, okay? Because we want all of the p orbitals to line up perfectly all the way around, so that way we can just draw resonance structures for days, right? If they're not overlapping, then you can't even draw resonance structures, so it's not conjugated, okay? And if it's not aromatic, then it does react like we might expect a normal alkene to react. So after adding Br2 to the cyclooctatetraene, we get the addition product where we have two bromines added across that pi bond, okay? Unlike benzene where you just substitute, okay? And let's see. I really want to just kind of hammer in there, just showing you that the conjugation that we can draw on this two dimensions is not there, okay? Just because you have every other bond as a pi bond doesn't mean you can actually have the resonance structures like we see. And that's, again, because the fact that this is not a planar compound. So remember that cyclooctatetraene is not planar, and it undergoes typical addition reactions, okay? So the next of the four criteria is conjugation. So I know we just mentioned that something needs to be conjugated in order for it to be aromatic. And if something's not planar, then it ruins that opportunity, right? And I do want to point out again, it has to be completely conjugated, right? Because that non-cyclic hexatriene was conjugated, but not completely. And by completely, I mean, can it go in a circle? Okay. So same thing with this cyclohexadiene, right? And then this cyclohexatetraene, they are not completely conjugated. And the cyclohexatetraene is not at all, because those p orbitals don't really overlap. But this cyclobutadiene, yeah, butadiene, that is conjugated and it goes in circles, right, for days. Okay. And so that's really what we want in order to classify something as aromatic. It's one of the four criteria, though, right? So after we've established that it's planar, cyclic, and is conjugated, what we want to do is determine if it meets the 4n plus 2 pi electron rule, okay? So benzene has 6 pi electrons, and that is 4n plus 2 equals 6, right? That's what we really want to think about. And how can we achieve this? We can when n is equal to 1. And we need to make sure that we have n as a whole number, right? So n is 0, 1, 2, 3, and so on and so forth. And that basically what I do is I take a number, I subtract 2, and then I see if it's divisible by 4. And then that tells me if it's aromatic or not. Cyclobutadiene has 4 pi electrons. And so that doesn't meet that 4n plus 2 criteria. Okay. We needed 2, 6, 10, or 14, sorry. And so 4 pi electrons meeting the cyclic, planar, and conjugated criteria actually classifies this as an anti-aromatic species. It's a class of its own. It's not, there's three. There's aromatic, anti-aromatic, and then non-aromatic. So this would be classified as anti-aromatic. And it's actually, rather than anomalously stable, it's anomalously reactive. It's very reactive, okay? And the 4n plus 2, we again would classify that as aromatic. And those compounds are very stable. They can still undergo chemical reactions. They're just not going to do the typical ones that you'd expect. And they might require a little bit more force to make it happen, okay? So let's just, in summary, right? So to be aromatic, it must be planar, it must be cyclic, it must be conjugated, and it must have 4n plus 2 pi electrons, okay? And again, it has to be 0, 1, 2, 3, or a whole number after that, okay? And sorry, let me change that to blue just because I have it blue above. And then I'll make my anti-aromatic red. So in order to be anti-aromatic, we actually still have to meet the criteria for an aromatic compound. So it must be planar, it must be cyclic, and it must be conjugated. But when it comes to the electrons, we need to have specifically 4 pi, some, like, I guess I should say 4n pi electrons, okay? And so it could be 4, it could be 8, 16, so on and so forth, okay? And to be non-aromatic, it just needs to lack one or more of these criteria, okay? So like the hexatriene, that was not, it was conjugated, but not in a continuous fashion because it wasn't a ring, right? If you kind of did a resonance structure where you would be on one end, it would have a negative charge, and the other would have a positive charge. Whereas if you have the ring, you can go in a circle and it's all good, and then you get it repeating. And so that's pretty much it for the aromaticity. The next video, what we want to do is go over aromatic compounds specifically and help you classify them, and then introduce some really cool ones, some that contain atoms other than carbon. And so check out that next one. But I am gonna leave you with a solid joke real quick because it's been a minute. All right, so a marsupial fixed me an aromatic beverage by pouring hot water over cured leaves, and it was absolutely delightful, so good. And I asked how it was possible to make something so awesome at this level, and he was like, dude, it's all about quality of your ingredients, you know what I mean? The quality. And I was like, bro, this quality is quality. It's so good. No? Okay, bye.